So hello, my name is Scot Breitenfeld. I'm with the HDF group. And first off, is there any questions that you want to ask before I start my talk? Okay, so basically my talk is a lot of users, when they start using HDF5, have questions about how do I rearrange my data in the HDF5 format? So I have all this data that I want to write, but I don't know exactly how to organize it within my HDF5 file. And the big concern is how you get good performance by rearranging how you're organizing your data. So this talk is kind of going to go down to the fundamentals of HDF5 and how when you first decide to write your data and how you write it and where you write it is going to affect the performance you're going to have down the road. So let's try to give you a heads up of what to think about when you start to rearrange and write your own HDF5 data. So just a brief, let me start my slide. So let's just do a quick review of HDF5. So as we know, it's a structured container, so it holds all the objects. And let's look at some of those objects. So you have your fundamental objects, which is your data sets and your attributes. So your data sets just organize and contain the data elements. And then attributes are usually your user-defined type metadata. And then associated with those data sets and attributes are data space, which describes the logical layout of the data. And then you also have your data type, which describes individual data elements. You can also then organize your data sets and attributes in terms of links. You can have external links to data sets or attributes outside of the HDF5 file, or you can have them organized in groups. You can put your data sets and attributes in certain groups, and then just use those groups, those attributes to describe what those groups would be. So let's go back to a fundamental problem, which is very simple. So we just want to say we want to write 2D arrays of variables over time. So this talk is going to mostly focus on parallel aspects, so as opposed to scalar. So now let's just assume we have P processors that are arranged in row by column process grids. And we have time steps that we want to loop over from 1 to S. And then we want to write each of those arrays, 1 to however many a number of arrays that we have. We want to then create those arrays. And we can do two sizes of those arrays. We can do either their X, Y, so that's strong scaling as we scale up the number of processes, or we can have the size of them scale up with the number of processes that we have, and that would be the weak scaling. So once we have determined the size of those arrays, we can either then write the arrays or read the arrays back to or from the HDF5 file. So a very simple problem of just writing multiple number of 2D arrays. But unfortunately, there's some missing information that we have. So the first is, how do we represent these 2D arrays in the HDF5 file itself? Do we represent them as 2D arrays, 3D arrays, 4D data sets? And do we know the extents of these data sets a priori? How many dimensions are ordered? And do we want to put them in groups? And what order is the data written? Do we want to write them one after the other for these variables, or do we want to interleave the arrays, which I'll show later? And then finally, what is the physical storage layout? So how many physical files do we want to have? Do we want to split the data into multiple files and then use external links to link them? What kind of data sets are they? Are they contiguous or chunked? And finally, is our end goal then to compress the data? Another thing we have to consider is what type of file system we're writing it to. Are we writing it to a Lustre file system or a GPFS file system or some other newer object store system, which could impact performance and how you arrange your data? And then you have to decide if you want to use for the parallel case, whether you want to do collective or independent IO. So let's talk about the first type of performance hurdle that users sometimes come across. If you look at HDF5 reference manual, it's very complex looking interface. but that doesn't essentially mean that it's difficult to use. It just is complex because different users have different goals of how they want to use HDF5. So one set of users have the goal of doing a self-describing share-friendly data layout. So these applications usually tune performance and efficiency with the constraint of using a standardized file format. So for example, if you're using NetCDF or CGNS, they have a certain file format that you must adhere to. And these file formats are usually self-describing, where they do a lot of use a lot of attributes to describe what the data sets actually mean. Then you have your second set of users, which is just to write the fastest I/O possible. So in that case, these applications are usually concerned about doing checkpoints. So you essentially minimize the amount of metadata or the data that you use and describe it, and just write very large blocks of data. So the complexity of your HDF5 workflow then will be dependent on what your goal is in the end. Another source that you can find when you have performance variability, especially for parallel, is the underlying hardware that you're running on. You also have the impact of other users using the system. If you have a shared file system, if someone's writing a lot of data and using up a lot of the OSTs, that might impact when you write your data as well. And then the final performance variability is the property list. And there are nearly 180 APIs in the H5P functions. And what the H5P functions do essentially controls the properties in-flight behavior of HDF5. So there are about 100 H5P set functions. And so that's a lot of combinations that you can test to see how each of those perfect performance. And what we find is that when you first implement a HDF5 API and you see that you can put H5P default for a lot of those properties, that's what users typically do that maybe don't have a lot of experience, because it gets them quick and up and running. The problem is you don't really know what the effect of using that H5P or H5P underscore default actually does. And as this talk progresses, you'll see that using the default can really hurt your performance, or you're missing out on a lot of performance that you would get if you were not to use that H5P default and instead use some H5P set function to help get performance. So let's go back to the earlier example. So good news, bad news. There's several different ways that if we want to write those arrays in HDF5 example. So we can write the 2D data sets attributes, or we can combine those reads and writes into fewer 3D data sets. And then finally, you can write them into 4D data sets. We also have to decide whether we want to do chunking, if we want to use align the data in the file itself, what size metadata block size do we want to use, and whether we're going to use independent or collective or independent I/O. Ideally, we want all these wouldn't matter and the performance would be pretty much the same, but it does matter. So we wrote a test, Gerd did, to explore some of the HDF5 parameter space. And I provided a link here. It's on GitHub. You can download it and test it out yourself. It's called HDF5-IO test. Basically, it's a way to explore the parameter space of HDF5. So for example, you have in the inner ring, you can explore the 2D, 3D, or 4 dataset rank of those arrays. And then we have the slowest dimension, which I'll describe next couple of slides what that means. Then you can explore your storage layout, which is you can do contiguous or chunked. Then you can explore whether you want to initialize your fill values, meaning if you create a data set and you don't actually put any data, fill them with data, then HDF5 will automatically fill that with zeros or whatever if you specify another value. Now you can turn that off, and we explore what the effects of turning that off is, then we have, you can study your alignment in the file. Then you can study your metadata size. You can choose many metadata sizes to explore. That's this blue ring. Then you can also explore which library version bound you want to use. You want to force it to be the 1.8 version of the library or the latest version. And then finally, you have your MPIO operations, whether it's collective or independent. So if you look along a ray on this circle, each ray crosses a parameter space that you want to look into. And for this case, I think there's 190, I don't remember exactly, combinations that you can sort through. So let's go back to the IO pattern model. So you have your step-based IO pattern. You have two steps, step 1 and step 2 for this example. And you have 5 variables that you want to write or read. So you first create your group, step 1 and step 2, and then write all those variables inside those groups. Now you can do the option of collapsing those groups into a 3D array. So you have you have your step 1, step 2 groups, but now you've collapsed those into a 3D array, those 5 variables. And then the last option is to collapse everything into one 4D array. So here you have your time, your variables, and then the variable dimensions itself. That's what we call this step-based IO pattern. The other option is to use an array-based IO pattern. So here you arrange it according to the number of variables you have, which is 5. So you create those groups, and for each of those variables, you have your step 1 and your step 2 data sets, and you repeat that for all the variables. Then you can combine those variables instead and combine those steps for each variable. And then finally, you can combine all those variables into one array. So this would be your 5 variables, your 2 steps, and then the dimensions themselves. So that's what we mean by using an array-based IO pattern. Those are typical 2 type of patterns that users explore. So what we did then was do a performance analysis. So this is on Summit, and we did this week scaling. So we scaled from 42 to 2600 processes. And what I did was arrange each of those parameter spaces from the best scalability, which is here on the left, and then I arranged everything else to the least scalable, which had the least scalability in terms of performance. And the bottom is the average time. And you can see that each color corresponds. So this is each parameter space that we're looking at. So this is the rank, the step, and the time, whether it's contiguous, chunked, fill, whether it's the orange is, say, for example, is true when you fill it, green is you don't fill it. And the alignment, one is default, and I set an alignment. The metadata we didn't explore, and then different versions of the library, and then independent and collective. So if you look on the leftmost sides, this parameter space gives the best scalability. And what that turns out to be is writing all your data in a 4-rank array. You use chunk data sets with no fill values. You use the default alignment, and independent IO for the first few cases perform the best. And then you can also see the worst performing ones if you were to use your parameter space set here. So this is just the tool that kind of gives you, if you want to run on a machine, and kind of gives you an idea of if you want to explore different layouts and different parameters, it's a tool to help you do that. So let's look at a use case. So there's an application called HACK, which is a hardware hybrid acceleration cosmology code. And it has a ability to do an MPIO only implementation where they just write the data using MPIO. We also did an implementation using HDF5. And if you look at the number of processors on the x-axis and the write bandwidth on the y-axis, you can see that the red is the MPI performance, which is very good. compared to the HDF5 performance, which is not so good comparatively. And this includes both the time to open a file and close the file. So we were wondering what's the difference between these two, because underneath HDF5 uses MPIO to write the data. So why are we seeing such a large difference in performance between the two? Well, if you look at the access patterns for the two, they are quite different. So for the hack case, let's take processor 0, for example. This is the file location of each of those variables. So in this case, it writes 9 variables, 9 arrays. And rank 0 will write its first variable, then it will write right after that, its second variable, and all the way up to 9. And then the rank 1 will start right after the last offset, where rank 0 was, and write in continuous blocks each of those variables. And that continues up for all the processors. Now, if we look at the HDF5 implementation, now this is what most users would do, is you have a rank 0, and what it will do is write its variable at a certain offset at the beginning of the file, and then it will skip to another offset to write the second variable, and then skip to the next offset all the way up to the last variable. Then rank 1 will start off at the offset where rank 0 started and write its variables. But you can see there's quite a jump between the offsets for each, where each rank has to write their part of the variable. Now you can kind of mimic what MPI is doing if you use a HDF5 compound data type. So here you have your part 1, which combines essentially all your variables into a compound type. So you can see that it will write very similar to what's happening in the interleaved. So this was what we call the interleave, because it's interleaving the variables. This is what we call contiguous, because it's essentially doing contiguous writes of all those variables. This is the typical. So if you have a hyperslab and each processor is writing a hyperslab part of that array, this is what you're going to see in your file. So how do we explored how we can match the pure MPI performance. So for that, we first determined the best stripe size and stripe count using the pure MPI implementation. And then we decide which data layout gives the best performance. So we have Lustre. We found out that the MPI contiguous individual is better. And on GPFS, we have the MPI interleave is better. So we essentially wanted to then tune HDF5 to match the performance of each of those MPI implementations on each of those file systems. So to tune HDF5 to match the MPI performance on Lustre, we set the metadata block size, and then you can see that the write performance on Lustre, the MPI contiguous performed the best, whereas HDF5, if you write individual, performs just as good as writing the MPI contiguous on Lustre. The worst was the HDF5 compound, and then the HDF5 multi, and then the interleave. So those two gave the worst performance. Now it's completely opposite though if you run on GPFS, where now you have the MPI contiguous and the HDF5 individual performing the worst, whereas the HDF5 compound is then performing the best. So the underlying file system can play a big part in how you're writing your data or reading it. So in conclusion from that study, you can see that HDF5 doesn't have a inherent way to match the MPI interleave access pattern. We did you can get similar with the compound data type, but for a lot of users, they can't really use compound data types. So we did experiment with having a type of MPI interleaved HDI, which we call HDF5 multi, which is an experimental way of writing that interleaved data on and we found that was performed very well on GPFS, just because the stripe size is small usually on GPFS, and users, you can't have any control over that. But for the contiguous, which is the HDF5 individual, we saw that was better on Lustre, because we use basically bigger stripe sizes and smaller stripe sizes on the file system. So you can see that not only do you have to tune HDF5, but you have to match the file system itself, especially on Lustre, with what you're actually doing your IO patterns. It's another thing to think about when you're using HDF5. And the last feature is metadata plays a large, very large role in the performance that you will obtain in parallel on parallel systems. The issue with metadata, so you have the metadata itself, which is an HDF5 feature, which describes the object headers, local global heaps, and Beano trees. And these metadata that HDF5 creates are usually small. We're in kilobytes compared to the raw data. When you're on a parallel file system, these small reads and writes can kill your performance, because in general, parallel file systems do not like small reads and small writes, and especially not when you're doing a lot of them at a time. So it's best to try to combine those metadatas. So we also have issues when the users themselves create a lot of metadata to describe the data. So use lots of attributes and data sets small data sets to describe their data. That can slow down the performance of your H5F close. If you're seeing that your raw data is going quickly, and then you're spending forever in closing the file itself, then that's probably an issue with the metadata. And you can help improve that by gathering all the metadata using these next few collective metadata functions. So basically, you can set your metadata to be collective, meaning that all the processors, usually they send it to one process, to their metadata to one processor, and then that one processor writes the data. You also have the same thing for metadata operations, where essentially you can do the same thing. And that really helps to speed up the performance of metadata writing, and it should help the performance of your file closes, or even your file opens when you want to read it. And then you can check to see what property mode you use by the get functions. So this should help your performance. And this is just an example of the CGNS code, which is a CFD standard, where if you don't use the version, this is so that we scaled up from the number of ranks from 128 to 16,000. Now, if you don't use these collective operations, you see the blue curve, which is, I mean, it's almost 2 minutes here to close a file. If you use that, it's basically nothing. So Lustre, this was both the case for Lustre and GPFS using these new functions. So this can really help performance of your code when you use collective metadata. Sorry, I went kind of quick. Is there any questions?
Yes, I had a question. This is Robert. You had mentioned that some users can't use compound data types when they're looking at improving performance. Is that because the data spec that they're working with doesn't allow it?
Right. Like if you're using XDMF or something like that, then it doesn't allow a compound data type.
Okay, yes.
Not expanded. Mm-hmm.
Got it.
Yeah, and a lot of the users, I mean, there are some drawbacks with the compound data types. If you can't just read, you have to isolate. Yeah, most of your packages, visit and stuff don't handle those type of compound data types. So you have to extend it, but that's usually why people don't use it. Mm-hmm.
Is that more of a retro consideration as people have a little bit more flexibility as they use later versions of HDF5, perhaps that constraint goes away? In other words, is that a little bit of a legacy issue with some things that dissipates over time?
Yeah, and another thing is that users don't maybe write their variables in a struct, so which is kind of a natural description of a compound data type. They keep it in arrays, so they'd have to pack it into a compound data type if their data structure or application was really kind of array based and not a struct kind of based. Then they'd have to create these compound data types, which would use up a lot of more possible memory. And they don't want to do that. So they just write people like to just write the arrays themselves if that's what they're doing.
Yes, I see. I see. Okay, that does it for me.
All right.
Thank you very much. Thank you very much.
Yeah, if no one else has any questions, we can wrap up. Thank you, Scott, so much for jumping in and presenting today.
Right. Thank you.
Thanks,
Bye.
everyone. We'll see you next week. Bye-bye.